Hello, greetings from the HLSL compiler team. My name is Greg Roth. I am a member of that team, and I am going to tell you about Shader Model 6.6 and how it can help you to build better shaders. So first of all, in idle moments, you may have wondered, where do shader models come from? And the answer is we simply cannot come up with this stuff on our own. Much as we wish that we had our finger on the pulse of the game development industry, we have to rely on you, the developers, to tell us what is needed, tell us what your pain points are, and in order to motivate us to solve them. So once we have collected those, and sometimes we receive, well, we always receive more than we're able to respond to, and we've collected some that make sense, we go to the hardware vendors and we work on finalizing them, hashing them out, defining the specifications and such. And then we each go to our corners and develop them for PC and Xbox. That's the driver, the compiler, and also the runtime component. So today I'm going to tell you about our latest shader model and the features that it includes. And this here is the basket of features. We've got 64-bit integer atomics, dynamic resources, helper lane detection, compute shader derivatives, 8-bit packing operations, and wave size. So first of all, a bit of a refresher. So a term that I'm going to use repeatedly here is intrinsics. Now, what is an intrinsic? An intrinsic is a function, but unlike a function that you might write yourself, where you can go and look at the code, or that somebody else might have written, you can go and look at how it's implemented. Intrinsics tend to be implemented in hardware. So there's not really any code that implements it. It's a single hardware instruction. At least that's the ideal. There are certain cases where we need to do some degree of emulation if there isn't a single hardware instruction that implements it. And so that can be done on the compiler side, on the runtime side, or on the driver side. At any point, they might decide, okay, for this platform, this isn't going to work. So we're going to do something that is optimal for this platform, but not as simple as a single hardware instruction. But the take home is that intrinsics are always better to use, even if you're able to implement it yourself. So the first feature we're going to discuss that introduces a lot of intrinsics, as all of these do, is the 64-bit atomic operations. Now, this is a very exciting feature, but it's pretty easy to explain because, put simply, all the existing atomic operations that previously required 32-bit integer parameters can now be used with 64-bit integer parameters. And it's almost that simple. And what this gives you is cases where you had more than 32 bits of data that you needed to update in conjunction with itself. You no longer need to insert a spin loop or do something equally inefficient. You can just use a single operation to upload the full 64-bit value. And here we list the intrinsics that have this new treatment. First of all, we have the interlocked add, and, or, XOR, min, and max. And then we have the various interlocked exchange and compare exchange parameters, or intrinsics. Now, where this does get a little more complicated is in terms of where this is supported and where this isn't. So 32-bit integer atomic operations are supported on essentially three kinds of data. You can think of it as three kinds of data. You've got your raw writable buffers, you've got your typed buffers, and you've got group shared variables. Now, what you get for free with Shader Model 6.6 is the ability to use this on raw buffers, that's byte address buffers and structured buffers, and also, when they are bound to the root signature. So if you want to use buffers or any resources that are part of a descriptor table, you will need to query this bit, which is actually in the options 11 structure. If you want to use typed resources, you'll need to query the bit that's listed here. That's so typed buffers, that's RW buffer and RW texture. And for group shared variables, they also have their own capability bit that needs to be queried in order to check whether you can make use of these or not. And that's pretty much it. So this is a really exciting feature, but it really doesn't take very long to explain. The next feature is dynamic resources. And this is another really cool feature. What it is, well, first, let's get a little background. Descriptor heaps. So a descriptor is essentially just a handle. It's like a code word that is used to communicate between the software and the hardware as to what object is being referred to and the memory that is backing it. A descriptor heap might actually be better called a descriptor array. It's just a sequence of these that are occasionally used, and they're certainly loaded and processed in conjunction. And so what the different kinds of descriptors are, of course, you've got SRVs, UAVs, constant buffers, and samplers. Now, samplers are kind of weird. They're always going to be a little off to the side. And so for this reason, all along in the API, you had to set up your resource heap in one place and your sampler heap in another place. And that's going to come into play here in a minute. So what are dynamic resources? So previously, when you wanted to set up these associations at runtime, you had to do some really complicated and brittle things. You had to set up a bunch of overlapping arrays, and it was very specific to the shader that you were working on at that moment, and you couldn't really port it around very easily. And dynamic resources just gets rid of all of that. And the way that it does this is it introduces these global arrays that have sort of a fuzzy notion of type. So instead of saying, okay, I've got this array and it contains RW textures of type float4, you just have a big array that has any kind of resource you can imagine, and there are different kinds of resources right next to each other. And you can index directly into that array in order to get access to your resources. And this allows live in-shader determination of these resources without having to use the really complicated root signatures that were necessary before. So here is a simple example of this. So in the comments up there, we have sort of a fuzzy idea of how these built-in arrays are defined. And we've got the R and the S type, and those are the fuzzy types I was saying, that R is kind of any resource you can imagine, and sampler is any sampler you can imagine. And well, you index into it just using an integer, as you might expect. And here in the example, we've got a constant variable ID, which is used to index into the resource descriptor heap. Now you'll see in the root signature here, we don't set up any UAVs, SRVs, or CBVs. It's all just a flag. Now this flag is probably unfamiliar to you because it is new, and it is required in order to make use of these just to give an indication, hey, look, I know I haven't specified any resources, but they're coming. And in this case, we simply index into the resource heap to get the resource, index into the resource, and return it. Not a very useful shader, but it kind of demonstrates the example. Now, where this does get a little more complicated is non-uniform indices, because non-uniform indices always complicate everything. So if the index varies within the wave, that is to say the wave is the number of threads that are executing in concert, the expectation is that that index is going to be the same for all of those threads all across the wave. So what an implementation very well might do is just take the first thread, determine what the index is, and splat that across the entire wave. And if your threads here on the end are expecting a different index, that's going to give you the wrong results. And this is why we need an intrinsic that is already existing, but you're going to need it for this case if you want to index into this array. And that intrinsic is called non-uniform resource index. Now, this is a bit of a pitfall because a lot of people think, oh, great, okay, an intrinsic, I'll call it, I'll assign the value, and then I'll use that as the index, and then we'll be good. It doesn't work that way because it's a little more complicated than that, and you need to apply this intrinsic exactly where you're indexing, exactly where you're reading it. And so this is something that occasionally people run into, and it's true here as well. So here we see an example where instead of taking the index from a constant variable, we're taking it from a parameter to main, which is always going to be non-uniform. Well, it's usually going to be non-uniform. And so we have applied that non-uniform resource index intrinsic in order to work around that problem so that even if every single one of them has a different index, this will work out. So there are some changes as well on the API side in terms of how you need to set these up. So first of all, and I alluded to this before, the root signature needs a special flag in order to indicate that the descriptors are going to come directly from the heap as opposed to being specified in the root index. So there are two variants of this. One is for samplers, one is for CBV, SRV, UAV, which is to say resources. And the additional requirement that this instills is that previously, if you wanted to set your descriptor heaps and then set your root signature, you could do that in any order that you preferred. It didn't really matter. It was all resolved in the end. But now you must set the descriptor heaps before you set your root signature. So here we see an example, and at the very ends there, we've got redundant set descriptor heaps. And the point that I'm trying to make with this is that that last one is going to have no effect unless you add another set root signature to the end there. So the next feature is helper lane detection. And this is this is to get around a dicey problem that we have run into several times over the last year. So first of all, a bit of a refresher. Lanes and quads. So I'm going to refer to lanes and threads interchangeably. In some contexts, they are distinguished. For my purposes, we're going to consider them to be the same thing. So a lane is a single thread of execution with its own state and its own outputs. The best example, the simplest example, is a pixel. A pixel is a single point on the screen. right there. Everybody knows what it is. Everybody knows what the output is. And you can imagine that, okay, every single pixel is chugging along, calculating everything, doesn't really care about what the other pixels are doing. It's got its data and it's going and doing its thing. And as I mentioned before, these pixels are actually executed in sequence. This is just the way that GPU hardware works, is that you've got a wave, which is a big collection of threads or lanes that get processed all in lockstep with one another. So for the most part, these are independent. Where the exception comes in is where derivatives or gradients are required. And then you need a little help from your friends. And that is where quads come in. So a quad is very simply just 4 neighboring lanes. It's in a 2x2 configuration. So these are used for explicit derivative calculations and also for the implicit usages for various sample operations to determine bitmaps. So because they require this information from their neighbors, they have to be at the same point in the program, of course. For this reason, all the members of a quad have to be in the same wave, and that's going to become important later. Additionally, as some of you are probably aware, you can use the quad read operations to access the variables of your neighboring quad members as you prefer. So we've got a diagram here just showing that's an example of a quad. It's pretty simple, 2x2, and one element of it is a lane. And then we have a hypothetical 32 component wave consisting of a bunch of lanes. So what are helper lanes? In pixel shaders specifically, sometimes you're taking your render target and you're dividing it up, and you've got each section being a 2x2 quad, but you're rendering a triangle, and it doesn't perfectly overlap a bunch of quads. So for the example, we see the diagram here, and you can see how the triangle doesn't quite cover all four members of the quad. And for this reason, now the three lanes in this example are able to compute all of their individual calculations by themselves. But when they need to get bitmap information, they need to know what that lazy fourth member is going to be. And for this reason, we fill in that empty space with something called a helper lane. And it is mostly invisible to the shader author. Render target writes are disabled. Any writes to UAVs, they're all disabled. There's no writing possible, and most wave intrinsics ignore these. An additional way that you can get this is if you decide to discard one member of a quad, then again, it converts into a helper lane because it still might have to contribute to these derivative calculations. Okay, so what we're building to is helper lane detection, because in some advanced usages of the wave operations that have fairly recently been added and have been used to great effect, will require knowing when something is a helper lane or not. Otherwise, you can get various infinite loops when you're trying to work around non-uniform variables and such. And for this reason, we found it enormously helpful to introduce the isHelperLane intrinsic. Put simply, what this does is it just returns true when you're helper lane and false when you're not. It's just that simple. And we found this to be so useful that we did one of those emulation things or software only fallback implementation for previous shader models. So starting with the new runtime and starting with the new compiler, you're going to be able to make use of this in all shader models from 6.0 and up. And what's more, the way that we implemented this, you might be thinking, well, I don't want to deal with that old inferior software implementation. In fact, the way that implementation has been done has been such that the hardware vendors and their drivers are probably going to be able to detect that, say, you're trying to do isHelperLane, here you go, swap in the isHelperLane information, which all of them have because all of them need it in order to determine what gets to write to something and what doesn't. So it's just a matter of exposing that to you so that you can make use of it. So the next feature, and also related to quads, as we will see, are compute shader derivatives. So 2D image processing at this point is sometimes done in compute shaders, and it would previously require you to calculate your own derivatives because you don't have these derivative operations in compute shaders. And so what we've done is we've added them to compute shaders, and the list of intrinsics are here. Here on the left, we see the direct derivative operations, ddx, ddy, and the coarse and fine derivatives. And on the right, we see sample operations that were previously unavailable. So there were some sample operations available in compute, but all of them required you to specify the gradient or specify the level of detail that you wanted explicitly, which required you to kind of do your own thing in order to calculate those derivatives, which again, you're perfectly able to do, but it's not as quick as when you can take advantage of the hardware. So we've got sample, sample bias, sample compare, and calculate level of detail, which, okay, it's not a sample operation, but it's close enough. So that sounds really simple. It gets complicated when you ask yourself, wait a minute, what's a quad? Because in a pixel shader, it's really simple. You take the render target, you divide it into 2x2 blocks, you fill in the gaps with helper lanes, and you're good to go. With compute shaders, you don't have a render target. You don't have an obvious two-dimensional space with which to coordinate your lanes or threads, usually called threads in compute shaders. So we needed to devise a way to define these quads for the sake of compute shaders. And we came up with two different ways of doing it. So first of all, if you just want to say, hey, look, I've got a bunch of lanes, I want to execute them, and I want them to be, per quad. So one quad, next quad, next quad. You can define a one-dimensional group thread shape, which is the way that we've decided to do this, because the numthreads attribute, it's pretty close to a render target in terms of how you're defining things. And so for here, the X component is the only one that's going to be anything but 1, and it has to be divisible by 4 because you're going to take those threads and we're going to divide them. Okay, the first 4 is a quad, second 4 is a quad, et cetera, et cetera, et cetera, until you run out of threads. And that's pretty straightforward. We're going to go into more detail on that in a minute. So the second method of doing this is what we call the 2D quad layout. And for this, the X and Y components are respected. The Z component can be whatever it wants to be. It's not really relevant in this case. And those have to be divisible by 2 because we're going to be doing something more similar to the pixel shader method, which is to say we have a two-dimensional block of threads, and we're just going to divide them into 2x2 blocks and call those quads and work from that. So it's important to note, these are your options. If you want to use quads in compute shaders, it has to be one of these two forms. Anything else and derivative operations are disallowed. They're not going to work. All right, so first of all, the 1D quad layout in a little more detail. So this is defined around group index, but in fact, because of the shape of things, the group index is going to be synonymous with the group thread ID, the X component of the group thread ID. And the way that this is done is very simply, so for each of those 4 components, you're going to take the first one, that's going to be the upper left, second one, upper right, third one, bottom left, fourth one, bottom right. Now, if you look at how this is done, it actually forms something like a Z. So this is sometimes called Z quad order. And we can see the example here. We've got a diagram of how the first quad in a big group of these might be laid out. Said a little more formally, the X position in the quad is defined by the least significant bit of the group index value, and the Y position from the top is specified using the second least significant bit. Now here we have some diagrams. What is interesting to note here is in the top 3 columns where we see how things are if you visualize them in 1D and how they are if you visualize them in 2D. And what I hope that this conveys is how important it is to twist things around in your mind so that you're thinking of these in 2D, because if you're trying to think of them in 1D, it just doesn't make any sense. So first of all, we see very simply just how the threads proceed in their indices from 0 to 3. And you can see that we've kind of formed a little Z there on the left. And then here in the center, we've got how a DDX fine operation works. And if you look at the 2D, you see, oh yes, okay, horizontal X component, that makes a lot of sense. If you look at the 1D, it doesn't make as much sense because it's just 0 to 1 and 2 to 3, and you think, well, why not 1 to 2? And then finally, in the Y case, this is where it gets really confusing because we're skipping all over and we're going 0 to 2 and 1 to 3 if you look at it in the 1D case. But if you look at the 2D, you see obviously, oh, okay, this is the Y component. And the final diagram at the bottom, this is just to demonstrate how quads proceed one to the other as you're proceeding through that X component or group index, depending on how you want to think about it. So, said a little more formally, the 2D quad layout, like I said, it's pretty intuitive if you just imagine a 2D surface and dividing it up into quads as you would expect. But said a little more formally, for every X and Y within the thread group that is even, both of them are even, the quad that they form is upper left XY, upper right X plus 1Y, bottom left, X, Y plus 1, bottom right, X plus 1, Y plus 1. And one thing that I wanted to mention is that previously there have been some assumptions on certain platforms where there is an association between the group thread ID and the wavelane index. We want to discourage you from making any such assumptions because there is no such association that should be assumed, particularly when making use of this feature. And this next slide makes a little more example of that. So first of all, we've just demonstrated how the group thread ID will be laid out in two-dimensional coordinates, as I've described. And also we see that EDX fine, it's perfectly understandable, 0, 0 to 1, 0, 0, 1 to 1, 1. And the DDY fine is doing the same, but in the vertical direction. Now here on the bottom is what I was saying before, where you've got these 2D quads, and each one of these that we have here is a valid quad according to the 2D quad layout. But they aren't adjacent to each other at all. They're pulled from all over the place. And yet I want you to imagine that these are all in the same wave. So the wave index would proceed from the upper left to the bottom right and would just have no association with the group index or the group thread ID at all. And that is a perfectly valid thing to do. I can't tell you if anyone does that, but it's something that you should prepare for. All right, next feature is 8-bit packing operations. Now, this is a fairly simple thing, but it is convenient. So recently, we have introduced various intrinsics, which allow you to perform operations on values that are 8 bits packed into a 32-bit integer. And so what we have here is something that allows you to take advantage of the hardware acceleration, or barring that, the best implementation possible, instead of having to use all the bit twiddling operations yourself. They exist, you can do it, but this is probably going to be faster. Now on the left, we see the pack function intrinsics, which are new, and we give you two options. You can take a vector of 32-bit integers or a vector of 16-bit integers, and you can pack them into unsigned 8-bit values into a 32-bit integer. That's what these types represent. We're going to go over that in a minute, or into unsigned. And so because we got two axes here, we end up with 4 intrinsics for the pack and 4 intrinsics for the unpack, which is the same thing, just in the other direction. So there is a variant for packing operations, which allows you to clamp these values. Now, the unclamped versions will basically just take your 8 lowest bits and put those into the value and ignore whether any of the other bits are set or not. So put another way, it ignores any overflows that might occur. Clamping operations will take those into account, and it will assign the minimum or maximum expressible value for your target type, depending. So here we see again the same 4 operations, well, variants of the 4 packing operations that we saw before. And in the comments after, we see what the ranges are. So for the unsigned, of course, you're clamping between 0 and 255. And for the signed, negative 128 and 127. And again, we've got 32-bit inputs and 16-bit inputs. Now, one thing that I want to emphasize, because this is something that has confused a few people, is that clamping always interprets the input assigned. So even if you're packing into an unsigned value, the inputs are going to be interpreted as unsigned. So the example that we give here where you might be a little confused here is that if you put in a -5 value, you might think, okay, -5 in an unsigned integer is way more than 255, so it's going to be 255. But it's not, because the input is interpreted as signed. Even though you're packing into unsigned, it's going to clamp to 0 and then pack that 0 into the unsigned value. So here's just a little note on these new types. These were done kind of as a convenience, the ability to communicate internally with the compiler and also to report diagnostics more accurately. They are, in fact, just straight type defs of the 32-bit unsigned integer. So if you don't like these types and you don't want to use them, you don't care about diagnostics, go ahead and use the 32-bit integers. It'll work just as well. All right, final feature, wave size. So once again, in keeping with the development that has been done on the relatively new wave size, wave intrinsics, which have been introduced in HLSL, some people have found it useful to customize their shader to expecting a particular wave size and not having to query what it is and iterate through them, but saying, okay, I have this really awesome algorithm, but it only works when the wave size is 32-bit, 32 elements. So there was really no way to do this. If you happened to be running on hardware where the only wave size available was 32, then you were great. You could just assume. But if you ever tried to run it anywhere else, well, then you got into problems. So this solves that problem by providing an attribute that you can specify for the entry point of a compute shader in order to say what wave size this shader is designed for. And if you try to run this shader, if you try to load it into a pipeline on a platform that doesn't support that wave size, you're going to get a validation error and it's going to fail. Ideally, that won't happen because you'll query it before, and we're going to get into the query in a minute. But here we see some example code, just very simple. It's an attribute. You put it before the main entry point. So wave sizes do have limits. You can't specify any wave size you could possibly imagine. First of all, it has to be a power of 2. It's not too surprising. And it has to be between 4 and 128 because that's just what's available at this point. In addition, the hardware that you have is not going to support any wave size in that range that you can imagine either. It's going to support probably a smaller subset of that. And the way that this is queried is with an existing feature bit, which is in options 1, and it is via the wavelength count min and wavelength count max. And what that says is, okay, here is the lowest power of 2 that I support, and here's the highest power of 2 I support. And anything in there, you can go ahead and use. So on that platform I said, where the only thing supported is 32, both of these are going to be 32. And so you query that, you say, hey, I can use my awesome 32 element shader, and you load it, and you get great performance. So as a bit of a recap, these are the required features for Shader Model 6.6. Now, I say that they're required. There are some prerequisites, at least in a couple of cases that you can see here, that are probably pretty intuitive. So first of all, if you want to use 64-bit atomics, you got to support 64-bit integers. If you're on a platform that doesn't, well, obviously you can't use 64-bit atomics because that's a prerequisite. Little less intuitive, dynamic resources, you do need to have resource binding tier 3. And these are queries that already existed. We're not introducing them. Helper lane detection, derivatives and compute shaders, 8-bit packing, and wave size, those are all have no prerequisites. They are included with Shader Model 6.6 no matter what. Now, as for optional features, you're going to see 64-bit atomics here a lot because of all the conditions that I said before. And once again, those are support for resource views that are in descriptor tables or on descriptor heaps, and 64-bit atomics on typed buffers and on group shared variables. And here again are the queries for that. And these are split between options 9 and 11. The descriptor table query is on 11, the rest are on 9. And finally, and this is one I didn't mention, in addition to supporting derivatives on compute, we can support derivatives on mesh and amplification shaders on platforms that support it, and there is a query there in options 11. In closing, I want to emphasize how grateful we are to the hardware vendors who have collaborated so closely and so helpfully with us on this. They contributed feedback to our specs, they entrusted us with important information that enabled us to do this, and they even provided fixes for the tests as we were going along. We are enormously grateful. We simply could not have done this without them. So we thank them a lot. So what's next for HLSL? The fact is we've got lots of awesome stuff coming, and I can't really go into much more detail than that. Suffice to say that we will continue to empower developers with the latest hardware features. We will continue to improve the language to make it more writable. And we will continue to improve the optimizations so that we can accelerate performance and reduce the size of the outputs. And finally, we want to mitigate your frustration by improving our diagnostics and improving our reliability, which is something we get a lot of feedback on and we're aware of, and we're doing what we can. That said, we need more people to help us in this endeavor. And if you or someone you know is a compiler developer and is interested, please go to careers.microsoft.com and search for HLSL. It will probably be the first hit. It might not look very descriptive, so be sure to read the details. All right, so a little more resources if you want to inform yourself a little more about this. So there is a blog post that I've written that accompanies this, goes into a little more detail, gives you the latest information and some other useful links. Finally, next, the HLSL compiler is developed. It's open source. It's in GitHub. You can go, you can look at all the source, you can make suggestions, you can check it out and make alterations yourself. It's all right there. And there as well, you can get the latest release. You will need to get this release in order to run Shader Model 6.6. The other thing you're going to need for Shader Model 6.6 is the latest SDK. And this is detailed in Jacques' presentation here in GameStack as well, which I encourage you to watch. It's all about the Agility SDK. And here again is a link to the blog post that accompanies that. So that is Shader Model 6.6. I want to thank you very much for listening. Happy coding, and may all your bugs be shallow.